Stoichiometry. What do we mean by stoichiometry? Here we go. Stoichiometry comes from the root word, it's probably Greek, which means to count things. And what that implies is that during the reaction, we want to keep track of what comes in and what goes out. For a number of reasons. One is we can predict the outcome, you know, especially if you're a chemical engineer and your bosses are saying, we want this process to produce this much money. And it can only do that if you're able to crank out so much product for a given amount of reactants that go in. So we need to keep track of the quantities of materials during a chemical reaction. And believe it or not, we can do that. But first thing we have to do is learn how to balance equations and learn what an equation is, how to balance it, because a balanced equation is the only way you can get to this budgeting of your reactants and products. Oh, it's German. Okay, I missed it. All right, first thing we need to do is learn how to count things that we can't see. Now, we can't see atoms, we can't see molecules. Some have been imaged, but not well enough to be useful to everyday chemists. So we're going to rely on a tried and tested method called counting by weighing. We do have very accurate ways of weighing our reactants and products that go into a reaction and come out of a reaction. So we need a connection between the weight that we measure and how many atoms and molecules does that represent. And that depends on which atoms and which molecules they are. So that's where dimensional analysis comes in. Keep track of the units because units are extremely important for doing this particular procedure. Okay, I already mentioned that. We have to, for practical purposes, treat the objects that we're counting as identical. In other words, this object should weigh the same amount as this object. But if you've got mixtures of different objects, like you have a mixture of, hydrogen and oxygen, right? The weight of oxygen, so many atoms or molecules, since oxygen's O2, right? So many molecules of O2 will weigh a certain amount. But the same number of molecules of H2 will weigh a different amount. But we have to assume that each one of those molecules weighs the same. Then we can react them together and produce, I've done this before, haven't I? What do we make when we combine those two? Water. But that's not balanced. We'll talk about that in a minute. Okay. So in order to say anything about the numbers that are reacting, we need to have an idea of what's the average mass of each one of these objects, these molecules in this case. And that's where we hit on the topic in the first exam material on molecular weight, or atomic weight, atomic weight. Right, see these numbers up here, these fractional numbers, 35.4532 for chlorine. That refers to the average, the weighted average of the mass of chlorine. Okay? Now we know because there are isotopes that they're all not 35 and they're all not 36. But the average mass is what we're interested in because we don't have the time and the equipment to count individual isotopes. They're just ludicrous. Okay, so here's my example. Say you have a pile of marbles, and you know that pile weighs 394.80 grams. You know that for sure. It's easy to measure that on a balance. But we want to know how many marbles there are in that mass, but we don't want to have to count all of them. So what we do is we just take a subsample, like 10 marbles, and we weigh those 10 marbles, and they're 37.6 grams. So how much does each marble weigh? If we're going to take an average weight of every marble, each marble would weigh a tenth of that, wouldn't it? 3.760 grams. And dimensional analysis time, if we say that 3.760 grams is how much 10 marbles weighs, right? Then we can use that as a conversion factor, right? Because whenever we see this ratio, we know from our past experience that this is equivalent to that. That's a conversion factor. So if we know the whole bunch weighs 394.80 grams, all right, we want to convert that to the number of marbles. How would we rearrange this? Remember, this is equal to 1. All right, so if we need to, we can flip it. So we need to cancel the grams, correct? That means the grams needs to go on the bottom. And the marbles goes on top. And that's perfect because the grams cancel and we're left with marbles. And that's what we wanted, the total number of marbles. So if we multiply 10 times this and divide by that value, we get the number of marbles to a pretty close approximation. I think I've got it here. Here we go. This one does it in 2 steps. We find out how much does each marble weigh. And then we use that information to find out how many marbles. But if you run this calculation, you'll end up with the same 105 marbles. Okay? That's called counting by weighing. Now the logical question is, that's fine, because we can count the number of marbles and weigh them. But when you're talking about atoms, you can't count the number of atoms and weigh them. So we're going to have to take a different approach. That's just weird. It works. Let me see if I got a better one in here. Yeah, microfiber cloth. Oh yeah, that's bad. Takes a little elbow grease. Okay, so that's our problem. How do we know the average mass of an atom? Well, what we have to do is pick a standard and just arbitrarily assign a mass to that particular standard. And by that standard, I mean, which one of these elements are we going to say and fix is exactly this amount? Deja vu. Did I mention this before? Okay, must have been a different class. So which one are we going to pick as our standard? Well, we know that in any one of these elements, they have a mix of isotopes. So we can't say that the naturally occurring mix of isotopes is a given weight. That just won't do. We got to pick out the isotope itself and say, this is how much that isotope weighs. And then all the other isotopes, all the other elements can be compared to that one. And that one turns out to be carbon. Carbon was chosen, actually, a long time ago. Oxygen was proposed. as the standard. It would set oxygen, the one oxygen isotope at 16 atomic mass units. The problem with oxygen is it's gas, right? So unless you have really good seals on your container and you're able to subtract the weight of the container, it's just a mess. You try to do a gas. So we eventually settled on carbon because you can get really pure, isotopically pure carbon with very little effort. And that one isotope, remember there's the mass number, that one is equal to 12.0000 atomic mass units. And then we compare everything else to that. Well, how do we do that? Well, it's kind of involved. Actually, the principle is very simple. It's Avogadro's law. And we haven't talked about gases yet, but I did mention Avogadro once, didn't I? Remember the two volumes? Like that? Did I mention that? Maybe I better do it again.
I'm just in traffic.
Okay, yeah, sign in, have a seat. And grab one of those, or just dump your stuff first and then come back. Can't do everything at once. So if you have these two equal volumes, this is what Avogadro said. And they're filled with gas. And it doesn't matter what the gases are. If the temperatures are equal, okay, and the pressures are equal within each container, and the volumes are equal, then the number of particles in each one are exactly the same. Okay, does that ring a bell? And we use this abbreviation, little n, without the zero. There's a little zero up there, it's a neutron. But with the little n, this is number of moles. We haven't defined that yet, but it's a number of particles. So using that relationship, if we have a gas of carbon in here, and you can do that if you heat it up enough, and then you have the same temperature over here with some other element, and they're exactly the same volume, and you weigh the two. Then you can compare the weight of this one, the weight of that one, because the difference in weight, the masses, are due to the difference in masses of the individual particles. Okay? So you know that with these conditions being the same, then the difference in mass is actually the difference in the mass of the isotopes. And if this one's 12, and that one, and it weighs a certain amount, and that one's weighs a greater amount, then you can set up a ratio and say, okay, each one of these has to be whatever mass comes out. And that's how you get the ball rolling. And you do that, you sort of do a cascade. It's difficult to get this into a gas, but once you've compared it to 3 or 4 different elements that are also gases, or liquids or solids, whatever the case may be, then you can start taking those and doing the same comparison, and you don't have to use carbon anymore. It's physically easier to do that. But this is our standard. That's where it starts, is with 12 atomic mass units. Now, the creators of this slide set use U. I like A and U, because U looks too much like Greek letter U. Could be anything. I mean, U by itself. It could be us. Who knows? So AMU is what I like. All right. Okay. We already know that. Naturally occurring elements can occur as a mixture of isotopes. So in order to do this, you've got to separate the isotopes, and the people that spend their entire lives doing nothing but this stuff right here. And a lot of them reside at the standards in testing. Brain fart. The ASTM, they serve as the governmental agency for standardizing this stuff, and they associate and they communicate with other national agencies the world over. Okay. So, naturally occurring, this particular isotope of carbon is almost all of the carbon that there is. And it's easy to prepare carbon. Okay, there's the other carbon. And there's carbon-14. Everybody's heard about that. Carbon-14 dating is radioactive. So, depending on the half-life, and I think the half-life is long enough so you can isolate that isotope and be pretty sure that once you're finished isolating it, you still got that much because it decays rather slowly. But once you've determined the mass of that atom relative to the standard, then you can calculate the average atomic mass that goes on the chart. Because it's 12.01078 is on this chart for carbon. That's because of weighting the average with these abundances. Okay, it's kind of like doing a GPA. A course that, if you get an A in a course that's only worth 1 or 2 credit hours, it doesn't carry as much weight as a 4-hour course where you get an A. That's the idea. Okay, so if we do the calculation, I guess I have to show you this. Otherwise, it would be on this slide. So if we take that abundance, and in order to avoid having to divide by 100, we just convert it to the fractional amount. And that's easier to do. But the fractional amount for carbon-12 is this, and the fractional amount of carbon-13 is this. And since carbon-14 is such a small amount, we're just going to leave it out. But the contribution that each one makes to the average, the weighted average, is this much, and this much for that. And then when you multiply those out and add them together, you get, well, that's an exact number. You get an average of 12.01. And when we do calculations in this class, 2 decimal places is plenty. And over the years, over the decades, those values to the second decimal place have not changed. If we were doing research where we needed more decimal points, then yeah, we'd have to check it periodically to see this upgraded. But for our purposes, just round to 2 decimal places and you'll be fine. Okay, that's the average atomic mass for carbon. Now, when you see carbon on the chart here, the periodic table, it's not going to be 12 because that's just for that isotope. 12.01, whatever. That's the weighted average for carbon. And that's the one we need as chemists because it takes into account the naturally occurring abundance of each isotope. All right. So this is just an illustration of how they do that. How do you separate those isotopes? This is called a mass spectrograph. And I won't spend a lot of time on it. If you really want to know how one works, I can give you a little more detail. But it's based upon the difference in weight of each atom. If you charge an atom, and each atom has the same charge, then it will experience the same force when it passes through a magnetic field. Right? So if the same force is applied to each atom, but you've got some lighter atoms and some heavier atoms, which one are going to bend more? The lighter ones. Right? So the lighter atoms, when they come through, when they're charged, and they pass through this magnetic field, the lighter ones are going to end up over here, and the heavier ones are going to end up here. Okay. And now we've got detectors that can count individual strikes on the detector, which corresponds to an individual ion or an individual atom. Okay, so let's take this example, and maybe we better not. Won't spend too much time on it. What we're saying is this element has been determined to have one isotope is 62.6%, and its mass is 186.956 atomic mass units. Okay, and it's already a fraction because it's compared to carbon-12. The only one that's 12.00 endlessly is carbon-12. That's fixed. The rest will vary and be fractional values. And then you've got the other isotope is this abundance, and it's that mass. So what's the average atomic mass? Let's see. I'm not sure if I did the calculation. There it is. So we take the fractional equivalent for the percent here times that one, and the fractional equivalent times that one. Add them together, and you get a value of 186.2. So that's the average atomic mass to only one decimal place. But what about it? What element is that? Right? We know how to identify an element using its number of protons. The atomic number. That's easy. But it's almost as easy if you know the mass of the element to find it also. Go to the periodic chart. From top to bottom, left to right, you have increasing masses. The same way you have increasing atomic numbers. And you just go along and you find which one matches that. And if we follow along here, 186.2, looks like rhenium is the closest one. There are a couple of places in the chart where atomic masses are very close together, so this may not be definitive. In most cases, and for your purposes, you can count on it. I'm not going to give you one that's really close. I can't think of one right off the top of my head. I know they're in there. Very, very close. Like cobalt and nickel. Right? They're only about 3/10 of an atomic mass unit apart. Anyway, so we can predict that's rhenium. That's not one you had to memorize. Okay, now I mentioned the mole. Right? The mole is not a little furry animal that digs in the ground. Not in chemistry. In chemistry, the mole is a number of things. And it has a history and a way to calculate it and refine the value. And that's what some chemists spend their entire lives doing. So we just have to take the value and run with it. We just have to know, what does the mole mean? Well, the mole is equivalent to the number of carbon atoms in exactly 12 grams of pure carbon-12 isotope. Okay? Now, how many is that? Well, it turns out, for our purposes, 6.022 times 10 to the 23rd. It's a huge number. It takes a lot of carbon atoms to equal 12 grams. And that's in honor of Avogadro. I mean, he didn't invent the number, but in honor of Avogadro, because of the methodology that's used to determine it, then we call it Avogadro's number. And it's a number of things. For our purposes, number of atoms, number of ions, number of molecules, right? But it's just a number. It could be a number of chickens. Okay, so 1 mole, this many carbon atoms, is equal to 12.01 grams of carbon with that mix of isotopes. it's based upon 1 mole of carbon-12 atoms. But 1 mole of carbon with not specifying the isotope is still this many atoms. And that many atoms won't weigh 12 grams, it'll weigh the average, 12.01 grams. So the beauty of this is that when you have a periodic chart, periodic table, and you know the atomic mass that's given for each one of the elements, that can either be that many atomic mass units for 1 atom on average, or it can be that many grams per mole of that average atom. And that's the one we want to use. Right? Atomic mass units is, you can almost forget about them, except remember it for the test. But for practical purposes, that number is the mass of 1 mole of those atoms. Okay? All right. Yeah.
So it's the mass number that's underneath of it?
Yes, these fractional numbers. Yeah.
That's equal to 1 mole of the
In grams.
in grams.
Right. So let's take, let's see, what about helium? 4.0026. That's helium. And that's naturally occurring helium with its mix of isotopes. It's already been done for us. That's equal to that many grams per mole of helium atoms. Right. Notice when you write the whole word out, MOLE, but when you abbreviate it, you just drop the E. Does that make sense? Okay. All right. We explained that already. So now notice this is a ratio, grams per mole. This ratio is a conversion factor. In other words, mathematically speaking, that's equal to 1. So you can use that conversion factor to make changes, to change units. And for this is one problem where you can do that. Iron atoms where you have 4.48 moles, 4.48 moles of iron. And you want to know how many atoms that represents. So you need a conversion factor that will cancel moles, right, numerator, denominator, and leave you with atoms. Well, we don't have to go to the periodic chart because that ratio is Avogadro's number. 6.022 times 10 to the third. Moles cancel, leaves you with atoms of iron. So you just multiply those out. And there you go. That many atoms is what that mass represents. And notice, like any other measurement, any other calculation, there is uncertainty. This still has 1, 2, certain numbers, certain digits, and 1 uncertain digit. The way we've presented it. It's got 3 significant figures, 2 certain, 1 uncertain. Okay? So that hasn't changed any since earlier chapters. It just tends to get lost in the fog as we proceed. Okay. So this is what we call the molar mass. And you can find it from the periodic table for any element. The weighted average in grams per mole of any element on that table. So what do we do when we don't have elements anymore? Suppose we have a molecule. all you have to do is add them up. You've got 2 hydrogens, then you would say 2 times 1.01 grams per mole plus 1 times oxygen. What is oxygen? Let's go look. Well, let's see, it's 15.99943. So rounded off to 2 places would be 16. Okay. All right, so 2.02 plus 16 is 18.02 grams per mole. And that's for water. Okay? That's how we do that. All right. How about this one? Well, I've already given you the answer. Messed up my animation. So when you have a parentheses and you've got a polyatomic ion, don't forget to multiply the subscript of the parentheses times whatever's inside. So in this case, 1 barium is here. Right. And we just put grams here. It's understood to be per mole. We've got 2 nitrogens. There we go. 2 times 14.01 is what you get off the chart for nitrogen. And then 6, 2 times 3, 6 oxygens. You just multiply and add those out, and you get 261.35 grams per mole. And that's the mass of 1 mole of this formula. Okay? So if you have 6.022 times 10 to the 23rd of these, it would weigh that many grams. Okay. I don't know why I keep this slide up here, because you don't even have to know anything except that an atom doesn't weigh multiple grams. An atom's too small to weigh. So by logic, this 1 copper atom ought to be that one right there. Right? This doesn't make any sense at all. One of those, though, would be the mass of 1 mole of copper atoms. Let's see which one it is. 63.55. Right? So that's the mass of 1 mole of copper atoms. And if you divide that by 6.022 times 10 to the 23rd, you'll get this value. All right. About the number of copper atoms in 63.55 gram sample of copper. This one doesn't even need a calculation. Right? We just said that that's what a mole would weigh, right? So the number of copper atoms would be 6.022 times 10 to the 23rd, correct? 1 mole. Trick question. Okay, how about this one? Which of the following 100 gram samples contains the greatest numbers of atoms? Now we're going to look at Avogadro's law a little differently. Before we said these 2 spheres had exactly the same number of particles, so if they weighed a different mass, then it was due to the number of particles. I mean, the mass of each particle. But now we're going to say we have the same number of atoms of each of these, right? Excuse me, we have the same mass, not the different mass, but the same mass. Okay, so now which one has the greatest number of atoms? Right? If each one of these weighs something different per atom, then which one would take the most atoms to make 100 grams? It'd be the one with the lightest weight per atom, correct? Because then it would take more of them to make 100 grams. So now all we have to do is look at, let's see, is that part of my slide? Well, magnesium is 24.3, zinc is 65.38, and silver is 107.86. So the lightest atom in there is the one that would be the most numerous to give you the same mass as the others. Right? Because if each one weighs less, it takes more of them to make 100 grams. Am I beating that horse too long? I think he's already dead. Yep.
So for the question before, the copper atomic sample,
Yep.
we wouldn't multiply the grams or divide it to get the, or would it multiply it by the atom?
Well, no, you don't want to make it any harder than it has to be. Right? 63.55 copper, 63.55 is the number of grams per mole. Right off the periodic table. And 1 mole is 6.022 times 10 to the 23rd atoms. So if you have that mass, you've got that many atoms. It's sort of a trick question. Because if you overthink it, then it'll twist your head around.
Okay, so but we're not converting it?
No, we don't need to, right? Because we can substitute in here 6.022 times 10 to the 23rd atoms. Right? Because these two are equivalent. 1 mole and that many atoms. So that mass is that many atoms.
Is that for all of them?
No, just for copper.
Oh.
We got that off the chart right here. 63.55. If we did that for say, I don't know, arsenic, 74.92 grams. For arsenic, would give you that many atoms. It'd be different for every element in the table. But
Avogadros would just stay the same as
yes. That's the definition of the molar mass. It's that mass for 1 mole. That's what molar mass means. Yeah. It's that mass in grams for a mole of those atoms. Okay? All righty. Okay, rank the following according to the number of atoms greatest to least. All right, this one looks difficult, but it's really not. If we're given 107.9 grams of silver and 70 grams of zinc and 21.0 grams of magnesium. So if we want to rank these from greatest to least, do we need to know the exact number of atoms? No, atoms is counting. Moles is counting too. So if we can say how many moles does each represent, then we can put them in order. We don't have to know the exact number of atoms. I mean, if you've got plenty of time and you're just curious, yeah, you could do it. But this many grams of silver is how many moles? Right. Off the periodic table, that's the molar mass of silver. It's 1 mole. Okay. How about zinc? 70 grams of zinc. Well, zinc is 65.38. 65.38 grams per mole. So what does that make this? That's greater than a mole. Okay. And 21 grams of magnesium, well, we looked at it before, 24.3. grams per mole. So how many moles is that? It's less than a mole. So we can put them in order from greatest to least. This one's greater than a mole. So this one's number 1. This one's equal to a mole. And this one's less than a mole. Greatest to least, right? Okay. I'm sort of introducing test-taking techniques too. Get it done quick, move on. Okay. A bit more complicated as we go, it looks like. For this one, consider separate 100-gram samples of each of the following. Rank them from greatest to least number of oxygen atoms. Okay, I say here, time for Henry Ford. What that means is we need an assembly line. What's the power of the assembly line that Ford discovered? You get your workers, each one, to specialize and do the same thing over and over. They get really good at it, and you move down the line. Either you move the workers down the line or you move the product down the line, which is what Ford did. And we're going to set this up so we do the same calculation over and over again to try to minimize error. We have 1, 2, 3, 4 different. We have water. We got dinitrogen monoxide, which is laughing gas. It's nitrous oxide. C3H6O2, which is propionic acid, probably. And carbon dioxide. Now, we're given 100 grams of each sample. We're just doing the same thing over and over again. We're going to need unit conversions because we want to know the number of oxygen atoms. Well, we can't tell the number of oxygen atoms until we've converted this to the number of moles, right? Because this is mass. We need numbers. So we need the number of moles of each one of these. And to do that, now we need to diverge just a little bit because each one has a different molar mass. And since molar mass is equal to 1, we can flip it. Instead of grams per mole, we're going to say moles per gram. Right? Still going to have 1 mole on top. Now we need grams. Water we did before, right? Remember what that value was? 18.02. Dinitrogen monoxide. So that's 16, right, for oxygen. And nitrogen is 14.01, so that's 28.02 plus 16. I don't trust myself. 4402. Okay. How about this one? Ooh. 3 times carbon. Carbon is 12.01. And hydrogen is 1.01 times 6. Just add them together. 3 times that, 6 times that, add them together. And then 2 oxygens is 32. 7409. Okay? And carbon dioxide. So we got oxygen, 2 oxygens is still 32. And carbon is 12.01. So that's 44.01. Okay? So that'll give us the number of moles of the compound. Okay? We want to know how many oxygen atoms that is. So we need another conversion factor. Oxygen per molecule. Oxygen per, I shouldn't do that. It won't be confused with mole per molecule. Okay. So this gives us the number of molecules. This changes the number of molecules to the number of oxygens. This one has 2. This one has 2. That one has 1. That one has 1. Okay. So grams cancel. Moles of molecules cancel. And this leaves us with the number of moles of oxygen. Okay? Let's see. I don't do the calculations in the hard copy, so you need to do that. All right, so now you've done all your thinking. The rest is just crunching numbers. So we got 100, and we divide by 18.02 times 1 is 5.55 moles of oxygen. 100 again. See, we got Henry Ford going here. 2.27. And 100 divided by 74.09 times 2. 2.70. And the last one. 100 again. 44.01 divided in 2 times 45, 44. No, 4.54. There we go. Okay. So we put them in order from greatest to least. This is the greatest. Next. And third, and then fourth. Okay. Did I lose anybody? Okay. So let's see, water, carbon dioxide, propionic acid, laughing gas. So there's your dimensional analysis example in the extreme. All right, this is just a reminder, problem solving. The first one, where are we going? For practical purposes, you can substitute in there. What's the question? Okay. Don't know what the question is. Not likely to find the answer. Know the question, then say, all right, what information am I given to solve this problem? I'm going to map out a course of action. Is it really simple or is it complex? If it's complex, chop it into little pieces so that you can work those pieces and then bring them back together to find the final answer. That's your course of action, your strategy. And if the information is not given completely in the problem, either you have to have it memorized, go to your periodic table, go to your useful information, or some other chart that's given to you to get the information. Because it may not all be right there in the problem. And then you check to see if your answer makes sense. So if you react, I don't know, 10 grams of sodium and 5 grams of oxygen, you should not come out with 4.4 million tons of product. That's an exaggeration, hyperbole for effect. So does it make sense? That's problem-solving strategy. Okay, so now we want to look at how do we express the composition of a compound? What is it made of? One of the simplest ways is mass percent, right? This element is so much percent of the total of the compound. And we present this one first because for a bench chemist, when they're analyzing a compound, this is what they'll come up with, mass percent. And it's simply the mass of the element that's in the compound divided by the mass of the compound times 100. Just that simple. So if you're given these values, right, it's a simple calculation. If you're given the mass percent, it's like any formula, right? It has three variables in it. You have this one, that one, and that one. If you're given two of them, you can solve for the other one. That's algebra. So a bench chemist works with raw material and determines the percent composition. But we can determine the theoretical percent composition if we have the formula. In this case, we have Fe2O3, iron 3 oxide. If we have the formula, we can also calculate what we expect to be the percent of each element. So the mass percent of iron, we just say, how much iron is there? Well, we need a standard, a reference. So we're going to say, we're going to stick to 1 mole. How much does 1 mole of this compound weigh? Well, there are 2 irons and 3 oxygens. There's your mass. 1 mole of that compound weighs this much. So if that's true, how many moles of iron are in there? Well, you only have this much iron, so you have 2 irons here. So this much iron and this much compound times 100. Okay? And it turns out 69.94% iron in that compound. Now we're going to learn how to go backwards, right? To go from here to there. If I can get to it today. So if we do percent oxygen by mass ranking, what we would do is actually, this last statement is important. And it brings up the comparison. Did I do the comparison of intensive versus extensive properties? Intensive property doesn't matter how much of the substance you have. It will not change, like density. Right? If you have a gold ring, it'll have a certain density. But if you have a big block of gold, it'll have the same density. Density won't change. That's an intensive factor. An extensive factor is one that does change with the amount. So the mass of that ring might be a certain number of grams, but a brick of gold may be many pounds. That's an extensive property. That's the reference I'm making here. Percent is an intensity factor, an intensive factor. So it doesn't matter whether we have 100 grams or 1,000 grams. Percent oxygen will not change, no matter how much we have. Oh, it doesn't show the calculation. Okay, so if you go back to that Henry Ford calculation and you say, what percent oxygen is in each one? You would say for H2O, okay, oxygen would be 16 grams, right, because there's only one of them in a mole, and 18.02 grams in a mole times 100. That would be percent oxygen. And you would do that for each one. And as it turns out, this is the highest percent oxygen is in water. The next is carbon dioxide, then propionic acid, and then laughing gas. But you do the exact same calculation for each one and find out how much oxygen is in that compound by percent by mass. And then you rank them. Okay. All right, so I mentioned that we were going to learn how to determine that formula from percent composition. We need a couple of definitions first. One, the empirical formula. The empirical formula for any compound is the simplest whole number ratio of elements in the compound. What I mean by that is, if we have this compound, which is acetylene, right? Torch gas. Or we have this one, which could be a number of things, but for my purposes, that's benzene. They would be exactly the same empirical formula. Right? What's the simplest whole number ratio of this one? Right? You can divide through by 2. Divide that by 2 is 1, divide that by 2 is 1. 1 and 1. How about this one? You can divide this one by 6. 6 into 6 is 1. 6 into 6 is 1. So they have the exact same empirical formula. Right? Now, if we just have this information, that doesn't help us much. Directly, it doesn't tell us which one of these is which. So we need a way to figure out the difference. Is it this one or is it that one? That's what we're looking for then, is the molecular formula. So if you look at it this way, and you say, this is our multiplier. You need to find that multiplier. 6 times 1 is 6, and 6 times 1 is 6, 2 times 1, 2 times 1. That will give you this formula. We just factored out the 6 and factored out the 2. That will give you the molecular formula, empirical formula versus molecular formula. Okay? Now, I'm not going to spend a lot of time on this because I don't have the time. But this is known as a reaction chain. And it's used to analyze particularly carbon-based compounds, carbohydrates and hydrocarbons in particular. And it just heats the sample up in a stream of oxygen and converts the sample to oxides, which are more volatile. And they will travel through the device. And in this device, you have a water absorber. Magnesium perchlorate is a good one. And it picks up the water and it lets the carbon dioxide go through. And then carbon dioxide over here is picked up with sodium hydroxide. Just flakes or pellets. And you weigh them before and after, right? There's a break here and a break here. And you just weigh this thing before, run your sample, weigh it after, and you know how much water is absorbed and how much carbon dioxide is absorbed. Well, oxygen's going through there, right? So you can't determine oxygen this way because it's in excess. But you can say, if we know the mass of water that's here, we can say, since we know percent composition, we can say that represents so many grams of hydrogen that came from our sample. And we know the mass of the sample too. So we know how much hydrogen came from that mass of sample, and we can ratio that in percent mass composition. We can do the same thing for carbon dioxide. And then if we've done a qualitative analysis beforehand, and we know that sample only has carbon, oxygen, hydrogen, nothing else, then by difference, we can determine what the oxygen is. That's just one example. There are a whole host of different tricks you can use to analyze your samples and determine their composition. This is one example. Okay, so we're going to take time to do this one. Let me see. We might have to spill over into Thursdays because we haven't even balanced equations yet. Maybe that's what we'll do. We'll finish this discussion on determining empirical and molecular formulas from the percent composition data. And then we'll stop there and pick it up on Thursday. Since I've got a buffer day built in for next Tuesday, then we will be cramped for time. And we'll balance equations on Thursday. Okay, so here's our example. We've got 49.3% by mass of carbon. We've got 6.9% hydrogen. And 43.8% oxygen. This is all by mass. Okay. Don't pay any attention to that yet. I'm going to use it in just a minute. We want to find the empirical formula. What's the simplest whole number ratio of atoms in that molecule? Well, percent, the problem with percent is it's a dimensionless number. It just means parts per 100. We know that it's grams per 100 grams because it's by mass. You have to know that. Otherwise, percent doesn't mean anything. So, but still, it's not in mass. There's no mass here, so we can't convert it to moles. So, are we stuck? No. If that's grams per 100 grams, let's assume that we have a 100 gram sample. Right? 100 gram sample. Right? That means we have 49.3 grams of carbon, 6.9 grams of hydrogen, and 43.8 grams of oxygen. Right? We can do that because this ratio is fixed, right? The law of definite proportions says that compound, no matter where it comes from, will always have that ratio. Okay, by mass. So now we know the ratio here by percent is equally as valid for mass. Now we can convert it to moles of each one of these that are represented in the sample of 100 gram sample of the compound. And once we have the ratio of moles, that represents numbers of atoms. And we can simplify it from there to the best whole number ratio. Okay, so what are our conversion factors? Carbon, 12.01 per mole. Hydrogen, 1.01 per mole. And oxygen, 16. Okay. So if we do that calculation for each one, 49.3 grams divided by 12.01. I get 4.10 rounded off. In that sample, 4.10 mole of carbon in that much sample. 6.9 divided by 1.01 is 6.83. And the last one, 43.8 grams divided by 16, 2.74. Okay, this is carbon, hydrogen, oxygen. Okay, we can't very well write 6.83, 2.74. Can't have a fraction of an atom. Right? We need to reduce this to some whole number ratio. Right? So how do we do it? Well, the ratio is established. That is fixed. This is true in a sense, but we want whole numbers. So the simplest way to do it is start with the smallest of the values and divide everything through by that same number. The ratio is still the same if you divide them all by the same number, right? So if we divide this one by 2.74, obviously we get 1. How about this one by 2.74? 2.74. We get 2.49. 2.49. How about this one? 4.10 by 2.74. 2.74. 1.50. Okay, we're getting warm. One of them's whole number. Now, at this point, we need a multiplier that will get rid of these fractions. And also at this point, you can start thinking in throwing darts. How close is close enough? Well, that's close enough to 2.5, 2.5. Right, so what can we multiply by all of those that will get rid of that half? What can you multiply by a half to get rid of it? 2. Multiply 2, and that half becomes a 1. So 2 times this one is 3, times this one is 5, times this one is 2. So there's your whole number ratio. Carbon, 3, hydrogen, 5, and oxygen, 2. This is the empirical formula. Notice that we cannot reduce that any further. That's the simplest whole number ratio. Right? Divide by 3, nope. Divide by 5, nope. Divide by 2, nope. That's the simplest whole number ratio. This is the empirical formula. Right? Remember my previous example. What we need now is a multiplier. But how do we know what the multiplier is going to give us? Where are we starting from? Well, that's where this value comes in. This is the actual molar mass of the compound. So if this multiplier is 1, then it's 3 carbons, 5 hydrogens, and 2 oxygens will be that number. But if it's 2, it'll be something else. What we need is, what does this represent right here? What value is that in molar mass? I call this empirical mass because we don't know that that's the molar composition yet. So the empirical mass equals what? 3 carbons, 12.01, 5 hydrogens, 5.05, and 2 oxygens, 32. That's 73.08. 73. For that formula. Right? So what multiplier, whole number multiplier, will give you 146 out of that? The closest you can get to it is a multiplier of 2. Right? If you multiply that by 2, you get pretty close to 146. So X equals 2. And that means the molecular formula is C6H10O4.
How'd you get it? The last one? The 2?
2 times 3, 2 times 5, and 2
Where'd
times
you
4.
get the 2 from?
Oh, 2. I got it from 146 divided by 73.08, and that's about 2. Because this is the empirical mass of that formula unit. And this is the empirical mass of this one times a multiplier, which we determined to be there. So if you ratio the two, you get this value here. And that's how we did it. See that movie, Young Frankenstein? Remember when Gene Wilder discovers his great-grandfather's private library? He finds this big book down there. And he holds the cover up and it says, "How I Did It." That's how I did it.
So at the beginning, where it says 100-gram sample,
Yep.
I was putting that over everything, but we're not dividing it by that 100-gram sample. That's just saying what it's equal to.
Yeah, the only reason that we assume a 100-gram sample is to get rid of the percent.
Right.
Because this right here, percent, is the same as grams of carbon per 100 gram sample. That's what percent means, parts per 100. And if it's parts per 100, then we can say with a 100-gram sample, we have that many grams. That's how we make the jump from here to grams, so that we can actually do some calculations. Otherwise, we're stuck right here. Okay. Let's see. I think this might be. Yeah. So let me make a note of myself. Let's see. We're gonna pick it up here on 8th.